let's get started. Jan, maybe slow into it and wait with the knockout punch until the end, but let's get going.
Okay, thank you, Martin. So then you allow me to share the screen. Yes. Okay, good. So I will talk about reproducible and transparent neuroscience and how the services that we are building in the Human Brain Project will be of relevance for these EBRA clusters and many more in Europe. So just to make sure we get the context right, what is EBRAINS? It is a European distributed digital research infrastructure for brain and brain-inspired research launched by HPP in 2019 and now growing and being stronger and stronger service. It provides tools and services assisting scientists in their research, collecting, analyzing, sharing, integrating brain data, and performing modeling and simulation of brain function. And we in the HPP will continue to develop this until our project ends in 2023. And the continuation is secured through the establishment of a new legal entity, the EBRAINS ASPL, which has at this point 7 member institutions investing into it, and of course then preparing for a future continuation in collaboration with many key players in Europe. So why? Obviously, to accelerate the effort to understand human brain function and disease through collaborative science, and also to secure Europe's leading position. We need to remember that there are many initiatives around the world. We interact closely with them, for example, through the International Brain Initiative. But at the same time, we should use the services we have in Europe and link them to the rest of the world, but also not just go across the Atlantic when we don't need to. So at this point, services available on the EBRAINS web portal are listed in this table. You might see a few things here and there that would be of interest, ranging from data and knowledge area, brain atlases, simulation, brain-inspired technologies of various kinds, medical data analytics, we'll hear on the next talk. On this occasion, only the left column will be the topic. So, why trying out EBRAINS data and knowledge services? Let's look at some possible questions or scenarios. So let's say I am funded by an agency that requests that I should share my data. And I wonder, can I get more out of that? Yes, you can through the EBRAINS data and knowledge services, because we make sure that you can publish the data, make them citable. In this way, you get credit. And there is also a license attached to each of the data in our system that you define as a data provider. Now, if you would like to make your data available with a journal publication, how does that relate to this service? It's actually specially prepared for that. So we have various sets of tracks prepared. You can choose the one that fits your situation, and also a special track for journals that are focusing on data sharing, including Nature Scientific data. We actually develop it together with them. Now, you may have data that is really of a foundational nature. You want to easily find back to them for your own use, and of course for others to use them and to cite them. Is then the EBRAINS data knowledge services relevant? It is, because it's specialized for neuroscience. It focuses on quality, and it does curation of metadata to increase the discoverability and opportunity for reuse. Based on 3 years of experience with this system now, we are introducing a new metadata schema for specifically neuroscience. Open minds is the term. This makes us now in a position to compete with a number of other fields, which will help you when you write your proposals, and you might compete with completely different fields. You can say that neuroscience is now in the same league. You could also be looking for research data to complement your own research. There are modelers, of course, who want to look at what's behind the table in a publication and so on and so on. And anyone can then easily discover the available data through what we call the knowledge graph search. So this is the EBRAINS.eu web portal. On that front page, there are several ways to find the services. And then they are sorted into some categories, one of them being the data and knowledge categories for finding or sharing. So here's what it looks like if you would enter the share data page, services. This is all built around not a conventional relational database, but a graph which can grow dynamically and which has the necessary flexibility to deal with a complex field such as neuroscience over time. It has key characteristics. It's open to the research community. It's based on a curation request procedure. Applying, takes 10 minutes to fill out and provide information, get an answer whether this is possible or not. And the accepted requests are provided with resources for curation and publishing of the datasets and models. And there are specific options to link this to journal publications. And there is long-term storage of these data provided in the petabyte range, which is part of the whole concept. So this gives certain advantages from left to right, data management support. We will also have a new facility hub launched in around the summer on advanced neurodata management, which you might find useful to save everybody's time and not writing up too many individualized plans when things can actually be streamlined. Long-term repository, proper credit, reuse, collaboration, and funding opportunities. It's all based on a very particular pipeline that starts with a curation request, goes through different steps with assistance and help on the way towards then the publication of the data and potential more in-depth integration of the data. Making data fair, as we say, findable, accessible, interoperable, reusable, starts with clusters of different data types that somehow needs to be curated and integrated in this knowledge graph, which is what we are helping every data provider with doing. And then there is this opportunity also to link the data to positions in the brain, which allows, again, that many data types can be discovered in a way comparable to geographic information systems by navigating the brain in 3 dimensions. And then working with tools and workflows, depending on the data type, of course, for the purpose of doing the research. This is also linked to the whole data sharing concept. So we have many types of collections of data at this point, more than 1,000 data sets from more than 1,100 researchers. How can they be found, accessed, used by the community? One would go to the find data pages, go directly to the search. There are filters of various kinds. There's free text search. You will find a data card for each collection. And this is all based on a sorting process that goes through this so-called knowledge graph and to the Open Minds metadata schema. From that data card, you can then either download the data or actually initiate something directly, or take the data into another space and work on it in various ways using the infrastructure. So there are many examples of using the data which are really key here. And I'd just like to emphasize or mention a few points through this simple diagram. On the EBRAINS.eu services pages, you can go into the atlases field and look at different types of resources there. This is where you can then combine the data knowledge services with various tools for analysis. There is the same thing on the simulation area, on electrophysiology data and so on, which allows different categories of data to be accumulated in the system and also to be used directly with the tools in the system. And you can also download these data and work with them on your own. So I hope this helps clarifies a little bit how this data knowledge services is built, why we have it, and what the advantages are. And I strongly believe we should interact closely, several of us, to look at opportunities in the near future. Thank you very much.
Great, thank you, Jan. Next up, we have Philippe Lebrun. Sorry, we're switching between screens. Okay.
Thank you. Good morning, everyone. So I hope you see my slide now. Do you? Yes, okay. So I'm going to tell you about the medical informatic platform, which is one of the services developed by HPP and integrated it in EBRAIN. Well, we know that brain disease at large, both mental health and neurological condition, affect about 1 person out of 2, 1 citizen out of 2 in Europe as elsewhere. So we're talking about 260 million people in Europe potentially with one of those disorder. Of course, unfortunately, not all severe, not all being followed at a hospital or university hospital yet, obviously. It's tens of millions of European citizens that do have medical record in university hospital. And there's a lot of knowledge and information hidden in those medical record that we can hardly share. There's a lot of challenge that has been discussed this morning. But basically, the reason I'm making that short introduction is to explain what the rationale that underlie the development of the medical informatic platform. It was finding a way to share more of this data primarily collected through clinical practice. Now, the MIP has unique characteristic as a platform for data sharing. It's GDPR compliant, it preserves privacy, and it's performing federated analysis, which mean, and that's the most important message, the data never leave the site of storage of origin. So if they are collected in hospitals for clinical practice, they will never leave that hospital. Rather, it's going to be the platform, the MIP, which is installed in the hospital, can communicate with other MIP. And the MIP is not just a storage place. It also has a number of algorithms, the same algorithm in every MIP, also the same data model in every MIP. And this is what allows you to perform different types of analysis, including machine learning, on federated data from a web-based interface without having to go through centralization of the data. It was primarily developed to share data across hospital, but it can be also used with other organizations as research lab, as public data set, of course, companies, and also other federated platform. Definitely a platform like the MIP needs to be interoperable, and there are other initiatives in the field of federation that we, of course, are aware of and are already collaborating with. Now, the MIP has had a long development since 2013, went through different phases. We, at the moment, at version 6.3. And since it proved to be robust enough over the last 2 years, it has been deployed already in 31 hospitals, and it gets medical record of more than 20,000 patients. So this is a beginning. We, of course, have the ambition to go at a much greater scale, but this pilot phase demonstrates the feasibility of the system. At the moment, we're working on use case, and some are already established, some other are being developed. The first one was in the field of dementia, with a few hospitals being connected also to some public data set, like the very well-known AIDNI. And it's moving forward. We're part of a new IMI project on neurodegenerative disease that will assemble 60 database. And it will also be linked to the so-called 80 workbench, 80 for Alzheimer's disease, which is funded by the Gates Foundation. So it's not just going to be the MIP, it's going to be the MIP, as I mentioned, interoperable with other platforms. We're also working in TBI. I will give you a very short snapshot on those two first use case in a minute. We're also working with traumatic brain injury, and actually we could here federate the two largest cohort that has been established in the world, the two in Europe. There are other in North America, but of a lower scale. It's the standard TBI one and the reactive one. And as you can see altogether, it's potentially 13,000 record prospectively collected in the field of TBI. And of course, putting those two cohorts together, which was difficult to start with because they had been competitive, one with the other, was challenging, but we get there, and we're now very happy to be able to have some kind of data sharing between cohorts. We also very much interested in mental health, even though at the moment it's just a pilot phase using the imaging data set. We're working a lot with epilepsy, and I'm part of EpiCluster, and so I'm promoting that interaction, especially with the European Reference Network EpiCare for rare and complex epilepsy. And now we're starting a strong partnership with the European Academy of Neurology. We will start with a few pilot, one on refractory status epilepticus, another one on stroke. That on stroke is, I think, a kind of a flagship for us. We aim at federating national stroke registry. Most countries in Europe have national stroke registry to follow on the activity of the stroke center and unit. And it's mandatory in some countries just to fund those clinical activity and make sure that the center have the appropriate level of quality of care. And so we really hope in the near future to federate those registry cross countries and to be able to compare medical practice and quality of care cross country. There's another project from the EN on narcolepsy, and we also in discussion with others in participating to establish the European Health Data Space, which is primarily based on federation. Now, importantly, there's different types of platform for federation, as I mentioned, but the way we designed the MIP has been very much looking for making data owner, data provider, being able to use the platform. Most data owner and data provider are not highly qualified data scientists. They are clinical researcher. And the more they can be involved in data exploration, the more they are likely to be motivated to share their data. And this is our strategy. So indeed, the interface is very intuitive, and I'm going to make a demo that really going to last just 1 minute. So I will share now my browser. Just 1 second. So to access the MIP for any accredited user, an accreditation is provided by EBRAINS through a complex process where any end user will be accredited both to a topic like dementia in that case and data set by the governance that is in place. And then you have basically 3 pages. One where you see all your metadata. They are organized as bubble to make it more simple to navigate. And then you can select easily by clicking on the different metadata. Here, for instance, we're discussing region of interest from the brain, and from which we have brain volume that has been previously calculated thanks to a pipeline which is available together with the MIP. Now, the second page, you see descriptive statistic of your different data set. Here, in that case, we are federating 3 data sets of dementia, one in Lille in France, one in Lausanne, CLM, and ADNI is a third one, a third instance, which is a very famous public data set. It's all online. If I remove ADNI, you see that there will be a refreshing of the data. That means it's calculated online. There are 3 MIP operating at the moment in 3 physical different places, and immediately I can get information on what data is available. Aggregated data. I cannot see individual data. I cannot see individual data set. I cannot upload or copy the data set. I can just make query for getting aggregated data. And then I can launch an analysis. In that case, it will be a logistic regression. And again, the 3 MIP are running the same kind of logistic regression on the same kind of variable that are previously selected. It's going to take a minute. So while doing this, I'm shifting just to another page. Okay, not even a minute. So I got my logistic regression. And to finish, the last 30 seconds, let me just share another federation. So when shifting from one to the other, I need to go to a different place. And here it's traumatic brain injury. It's just to illustrate that the metadata are completely different, much less. Why? It's because these 2 projects on TBI, as I told you, they were kind of competitive. So they had to agree on a subset of metadata that they will share together. And they have agreed on that very limited set of about 20 metadata. But here again, it allows to perform analysis. Here it's a little bit longer to get the result from the descriptive analysis because there's more data. But here we got it. So you see 4,500 cases from Center TBI. The MIP is at the INCF in Stockholm at the Karolinska Institute, and Creactive, which is in Bergamo. And then I can, of course, also launch analysis. In that case, it was to perform what we call a calibration belt. It takes 2-3 minutes, so I don't want you to lose time for this. I'm just showing you the result. And basically, it's just validating a predictive model of mortality at 6 months. And we could just show that by putting together the 2 cohorts, we get a better result, more precise result for establishing what could be the best predictive score. So those are just illustration of how easily it is possible to perform federated analysis. Of course, on the data has been curated, on the has been placed in a medical informatic platform in the hospital or research center where the data keeps stored, and how we can manage all the issue about data privacy and data safety in that case. Of course, all the data are to be anonymous to start with. Thank you very much for your attention.
Great, thank you, Philippe. Next up, we have Petra talking about the virtual brain simulations.
Yes, hello everybody. Let me just share my presentation. Can you see it now? Okay, so I'm talking about brain simulation at a service. The Virtual Brain Cloud is one of 24 infrastructure facilities of EBRAINS, as you can see here. So we have a distributed network of infrastructure serving EBRAINS. And the goal of the virtual brain is to do brain modeling, to integrate various sources of data in a theoretical framework and to understand the mechanisms that underlie brain function and brain disease. And for this, we have developed several different service categories in the past years. the virtual brain simulator, multi-scale co-simulation tools, optimized code for supercomputing, model fitting routines, pipelines to process radiologic imaging data, and then we have the data sets themselves. And this is how it looks when it is integrated in the EBRAINS platform. So all the service categories can be seen here in the blue column. And you see they're interconnected with other core services that you see here. So we have, for example, Drive, a file system for organizing data and controlling access. Then Wiki to create collaborative protected spaces for collaboration, Office for documenting the work, then Jupyter Lab as a programmatic front end, OpenShift to orchestrate workflows, and the high-performance computing backend. We also have the knowledge graphs. This has been already introduced by Jan in order to enable data discovery. And very importantly, for brain modeling, we require personal data. And rich personal data like MRI or connectomes cannot be easily pseudonymized. We have heard that from Damian before, and therefore they need thorough protection. And it has been mentioned in the chat, for example, the brain image library, which is based in the US. And indeed, several of such brain images, for example, the Human Connectome project, are freely available in the internet. And often they are associated with cognitive scores, with diagnosis, and many additional data. And most importantly, from these connectomes, for example, you can predict many other personal features of a person. For example, performance of working memory, performance of sustained attention, or even satisfaction with your own life. So this is highly personal data, and it needs to be protected. And for this reason, not so long ago, the European Union established a new law, the General Data Protection Regulation. And the GDPR defines 3 different roles. Data subject, this is the person behind the data controller who takes the responsibility and determines the purposes of processing, and the processor on behalf who processes data on behalf of the data controller. So very importantly, in Europe, we do not have data owners. This is data, personal data cannot be possessed by anybody, not even by the data subject. According to the law, Article 25 GDPR, the data controller needs to provide sufficient protection for personal data. And the data controller has to mitigate the risk for the data subject. And this is what we did for the workflows that are related to TVB and EBRAINS. So we established several mechanisms in order to provide sufficient protection for the personal data that are access control, encryption, and sandboxing. And I will show you with the example of one of the workflows how this exactly has been implemented. So this is a radiologic imaging pipeline that processes radiologic imaging data and brings them in the format that we need for simulation. It consists of 3 container images, 3 workflows that are contained in containers. The first one processes structural imaging data and generates the structural connectomes and some additional structural information needed to constrain our models. Then the second one processes functional data, and the third one then translates the outputs of the first and the second container in the format that we need for simulation. It also establishes all the security mechanisms that we need in order to process the data in compliance with GDPR. If we look a little bit closer, what has to happen? We have to transfer the data that we want to process in the EBRAINS cloud. They then go to the supercomputing centers. So EBRAINS is served by 5 supercomputing centers that are distributed across Europe. And this is an open shared environment. Then we have the programmatic front end that allows us to control the processes that run on the supercomputers. And the processes then are processing the data, and the output is transferred back to the cloud and can be accessed by the user. So what can now happen in such workflows? There are several risks, and this is just a very high level description of what can happen. So for example, there can be intercept during transit, there can be break-in on a device when the data are being processed, or if you lose your password or it's getting stolen, then a person can act on your behalf, user impersonation. So all these mechanisms lead to unauthorized access of highly personal data. What did we do in order to protect our data from such unauthorized access and to mitigate the risk for the data subject? Number one, we implemented encryption. So the data are basically all the time encrypted. There's a single exception. And for this, we implement another protection mechanism, which is sandboxing. What is sandboxing? Sandboxing is a technology that shields different processes. It's, for example, also used for the apps that you run on your smartphone that otherwise could damage your phone or access your personal data in the phone. And this is how it looks when it's implemented. So we have here 3 different network nodes. We have the computer of the data controller, we have the cloud of EBRAINS, and we have the supercomputing center, high performance computing. And the user can now establish such a secure sandbox on the supercomputer. The data controller also has a public key. So we use cryptography, public key cryptography. Also in the sandbox, a mechanism creates a public key from the supercomputer. And this public key created on the supercomputer will be used by the data controller to encrypt their data. And in this encrypted way, the data are transferred via the cloud to the supercomputer. They land in the protected sandbox environment that nobody can access. And only there is a private key and can decrypt the data for processing. So the data are being processed, then the temporary files are deleted securely, and the output data, the results, are now encrypted again using the public key from the data controller. And only the data controller has a private key. So in the entire life cycle of these data, only the data controller ever can access the data. So this is a very high protection level, which is necessary because we are talking here about health data, which is a special category of data according to GDPR and needs particular protection. And in general, its processing is actually prohibited. So you can only process it under certain conditions. So this was now an example how we established secure workflows on EBRAINS, a shared open environment where it is particularly challenging to make the data flow secure. I want to quickly show you another platform that we co-developed. This development started in April last year, the virtual research environment, which is from the scratch designed to provide a platform research infrastructure for sensitive health data. And this is established on the premises of the Charité and the BIH in Berlin. It's very similar to EBRAINS, you will see this, but it is in another environment. It's in a secure hospital environment. And this is how it looks like. So we have also a portal as we have in EBRAINS. This is, by the way, the URL via e.charité.de. This platform is open for external collaborators. So it's not only for Charité folks. And what is different from what we have in EBRAINS is, for example, the green room. The green room is a particularly protected area where data sources directly from the hospital, like radiologic images, electronic health records, can go, and they are getting de-identified there as far as possible for the research that has to be done on the data. So this is a secured environment where de-identification takes place, and the de-identified data then go in the core of the virtual research environment. And there you find the data warehouse, you find the knowledge graph as we have it in EBRAINS, and you find all the analytics pipelines that can be brought in by the researchers. And you have also the workbench concept that we have for EBRAINS as well. So this platform is already in production. It can be used and provides all the functionality. We are also working here with the knowledge graph from EBRAINS. So we have also the graph database. The data are open minds annotated. We have a visual graph explorer, and we have a programmatic interface to allow programmatic discovery of data. So this also allows a connection to all the digital atlases that are already available in EBRAINS, and we further enhanced that actually and extended this to be able to on the fly explore knowledge bases of pathway inventories. So it is now possible to retrieve in real time knowledge about signaling cascades and map that on the brain in the same space as we have our brain models, and incorporate this information in our simulations to make them even more precise. This is the network architecture of the platform in the secure hospital environment at the Charité. And I show that to you. You cannot read it, to show you the different networks, sub-networks that are separated. And there's a very strict restriction of information flow. So these different policies for the different zones in this platform serve the data protection. And the more sensitive the data are, obviously, the more protected they are. So how can you imagine working in such a platform for sensitive data? Again, it is similar as we know it all from EBRAINS. There's a portal, there's a single sign-on of the user. Data can be brought in with the addition of a green room where identifying information, like even clear names and addresses, can be still present, or birth dates. And there we have workflows where data are being cleaned up from this identifying information. And there will be an approval process before the data go in the core zone of the virtual research environment. And this is where the data warehouses are, where the metadata are being stored, and where the workflows of the individual researchers can access the data and work with the data. There are different deployments, again, as we have it on EBRAINS. There's a virtual desktop. This looks like this. If you start this, and there you find your desktop application. So for example, you can run the virtual brain directly via the graphical user interface in the secure environment of the virtual research environment. It looks exactly the same way as it would be on your computer, but the difference is the data are kept secure in the virtual research environment, and only these unstructured visuals, they are transferred to your computer. The data themselves stay in the protected environment. And here's another workflow, same thing, sign on of the user. You can bring in the data, but then you have the programmatic interface in form of the Jupyter Lab, Jupyter notebooks that you can start from the inside of the VRE. So this is the inside of the VRE. Here's a menu, and here you start the Jupyter notebook. And this looks, again, similar as in Jupyter Lab in EBRAINS, where you can then load your, for example, Python libraries. This is a virtual brain library, and programmatically run your workflows on your data in the VRE. This is a workbench concept that we have in EBRAINS with many different ways of deployment to be as flexible as possible and provide many ways for the researcher to interact with the data that are in a protected environment. So with this research infrastructure for sensitive data, the needs of the researchers are fulfilled to be able to store their sensitive data, to share their sensitive data, and to process their sensitive data in accordance with the fair data principles, to provide the privacy and security that is needed for such type of data, and to be in compliance with general data protection regulations. And we have an ecosystem development model where these platforms, the virtual research environment, EBRAINS, or the virtual brain cloud, are co-evolving and are being aligned. So they're using similar or even identical technologies in order to make them interoperable. And each progress in one of the platforms will benefit the other platform, and is directly portable as a solution for the partner platform. And with this, we hope to provide a safe environment for an increasing number of services for sensitive data. Thank you very much.
Thank you, Petra. And this gets us to Victor with the last presentation of today. Victor?
Yeah, I'm going to share my screen. I assume you can see. Martin, can you confirm that you hear me?
I can see and I can hear. Go for it.
Wonderful, yeah. Good morning, everyone. My name is Victor Yersa, and I was asked to speak about running simulations on top of clinical data, in particular along the example of epilepsy. And in this context, some of us were asked by Marissa in the beginning to provide some words of wisdom, yeah, that are representative to the message that we'd like to share. And what I emphasized is down here: integration is the foundation of actionable data. Looking deeper, integration is not just a collection of software tools on a fancy website, but starts with concepts and deep understanding of a process, in fact, of scientific question, and is then followed by the organization of tools and good practices. What I wanted to point out here is that we need to put workflows in place, and actually theoretically and conceptually driven workflows that allow us to generate a societal impact at the end, and a real outcome, a tangible outcome, and not just another scientific high impact paper, but a workflow that goes all the way end to end to the patient, for instance. And these workflows need to be organized not just informatically, but also conceptually. And I'd like to discuss this along one of the examples we have in EBRAINS. What you see here is the large-scale workflow that Jan was talking about earlier. One of the key motivations is to put knowledge and competencies that we have accumulated over decades in science and research in a digestible form, organize them and curate them within the EBRAINS data services, make them findable in the knowledge graph, access them hierarchically in order to then map them into a brain reference framework that can be navigated. Yeah. Here, along in the example of the Human Brain Atlas, in which we can actually make a direct link to the modeling services. So we're connecting data with a generative model. In this case, I would like to highlight the virtual brain that Petra just spoke about, that allows us to use it as a generative model to form what we call causal inference. And that allows us actually to build causal hypotheses about what is going on in a brain state, in a disease, and actually make predictions, yeah, also beyond what is contained in the individual data. So we go beyond statistical inference, which is typically being performed in the methods of artificial intelligence, and reach out to causal inference, being able to make statements due to its mechanistic nature, being able to make statements beyond the individual data to discover new avenues for curative approaches, for instance. Here we go. Yeah. So in the example of the virtual brain, we do as follows. We use individual brain imaging data. Typically from the anatomical MRI, we are able to reconstruct the topography, to parcellate the cortical and subcortical surfaces, to extract diffusion from the diffusion tensor-weighted images, the large-scale connectome, and co-register this in the same space to be able to build a skeleton that then can be equipped with mathematical models that we have developed over the almost decade in HPP, allowing us to migrate between microscopic, mesoscopic, and macroscopic scales of organization to address mechanistic questions, actually map the data. So we do, in a nutshell, we do the following. We reconstruct and parcellate the geometry. We collapse it into individual network nodes, which we connect with the individual's connectome. And then once equipped with mathematical models, we can generate synthetic data and measure them. For instance, in the case of epilepsy, we use a stereotactic EEG, but we can also not only develop this type of models on the source level projected to the SEEG, but also to EEG, MEG, functional MRI, to all modeling, to all imaging modalities simultaneously. This is a platform that we are talking about. And it can be done for multiple species. Here an example of the virtual mouse brain that you saw also in the previous presentation. And along this example, I can actually point out some of the predictive advantages that we can actually systematically explore. In the mouse model, we can not only use tracer-based data, in this case from the Allen Institute. By tracer-based data, we can reconstruct the individual connectivity of the mouse. We lose, like this, the individuality of the brain. However, we gain a high resolution and a gold standard of the truly existing fibers. But we can also put the individual mice then in the MRI scanner and actually go through the same strategies of data collection as we do with the human brain, and use different technologies for reconstructing of the connectome, such as deterministic diffusion MRI or probabilistic diffusion MRI. The key message of this study that I highly recommend, this is a 2019 study, is the following. We can build a set of metrics that estimates the predictive power. In this case, it was a functional connectivity. Others can be performed. You measure individual brain states. In this case, it was resting state activity. And in DLA, you find the scan, rescan variability of the same brain. And then you can actually reconstruct individual brains. The one on the highly detailed tracer-based virtual brain, and then actually reconstruct the functional data that can be actually observed by this model and compare it against the empirical data. Here we have scan, rescan variability almost and predictive power almost 60%, drops down to 50% from an independent model. And then the message here is, when we use the individual connectomes using different methods, we always have a better predictive power here, between 40 to 45%, than using some generic connectomes. And this you can do systematically and pull out individual features, etc., and reconstruct this. The message from this slide is we get biggest predictive power when we use high resolution, when we which is even bigger than personalization, but personalization is better than individual connectome. If we can combine these two, we have actually, in a large scale workflow, we can actually optimize our predictive power. And this is what we are doing in EBRAINS. We are building these large scale workflows for individual human brains, where the virtual brain of the human is informed by very detailed, high resolution data, either connectomics or coming from many different resources represented in the knowledge graph, informing the network nodes, and then going against a data fitting and validation process, typically using Bayesian inference or other methods of artificial intelligence, to set the parameters in the model to build a virtual brain that is personalizable. And here in this example, you see this for the example of epilepsy, where we have personalized an individual patient's brain going through the workflow. And once the person's epileptogenic zone was identified, we can actually run the brain model autonomously and reconstruct the range of individual seizures. These are simulated data that you see here, not just one single seizure, but the entire repertoire of the patient's seizures, measure variability, also infer parameters and manipulate the parameters. The current use cases for this autonomous in silico platform at the moment in epilepsy is surgery, the identification of the epileptogenic zone, but also other approaches in epilepsy, for instance, stimulation directly in the brain is one of the very upcoming and reversible approaches, which is also being used in cases of pharmaceutically resistant depression. This is another use case that we're working on. But more generally, it can actually be used as platform for the discovery of novel biomarkers of brain health, which is being done, for instance, in aging and neurodegenerative diseases, allowing us to reconstruct the brain health trajectory and assess the brain health of an individual patient. Finally, another application is the development of virtual cohorts, because on the basis of a patient, knowing a large-scale variability that is allowable to this, you can actually generate 1,000 or 100,000 patients that fall into the same type of category, each of them with all possible data and imaging modalities available. In this case, you saw the SEEG. This can be carried all the way to the patient. At the moment, there is a clinical trial ongoing using the personalization of epilepsy patients in drug-resistant epilepsy, involving 13 reference centers in France, in this case, with the data being collected over a period of 4 years, being centralized in the central database. And then the patient, on the basis of the patient data, they are being virtualized, passed by the pipeline that I just presented you, estimating the epileptogenic zone and providing a clinical report back to the individual reference centers in order to inform the clinicians treating the patient and actually influence the decision-making for the surgery. And at the moment, there were some COVID-related slowdowns, but we have recruited, the last time I looked was in February, 128 patients that have been included. More than half of them have been randomized. So we are already having first results with regard to this. And the resulting evaluation is the following. Based on the personalized virtual brains, you can estimate the epileptogenic zone as represented here in this particular patient. And then the resection is being performed. And 1 year after surgery, you have the evaluations. One last message here with regard to this. Times are still early, but first evaluations thereof demonstrate that there is a very good predictive value here. Something you may also a set of different evaluation matrix. You find AUC here, or precision or recall. So precision is actually very good. AUC is 75. So that is good. For the patients that we already have available that underwent the surgery and 1 year after, some of them have been seizure-free. For the 13 seizure-free patients, you see first clinician's evaluation, independent clinician's evaluation, clinical hypothesis, second clinical hypothesis of an independent expert, and the VP. This is a predictive power in terms of precision. So we are between 80 to 90%, and which drops down actually significantly for the virtual brain for the non-seizure-free patients where there have been actually failures. So this is a retrospective analysis of the prospective patients, but it points into the direction that we're going the right way. Yeah. So I wanted to share here with you is essentially highlighting the importance of the large-scale workflows that we are implementing in the ecosystem of EBRAINS. And there it's the interoperability of the data is not sufficient, and not sufficient neither just the availability of the tools. What we need to have is concepts down that allow us to build workflows that integrate model, scientific questions, data, the validation processes in a workflow that guides us all the way to the clinical trial and hopefully even to a commercial translation, so we can actually reach a large number of patients beyond the clinical trial. So real end-to-end patient solutions. And one of the emphases must be essentially the personalization of the in silico brain model. I'm stopping here. Thank you very much.